Dear all, so we are going to see today path planning for a robot. We use the A-star search algorithm to find an optimal path for a robot navigating a 2D grid. Our robot should move from a start point to a goal in a grid while avoiding the obstacles. We implement A-star with the Manhattan distance heuristic applies to grids without any diagonal movement, and Euclidean distance heuristic applicable to grids that allow the diagonal movement. We use the plotting library to visualize the found path, and we compare A-star with BFS and uniform cost search. So here is the program. So let us first run it. We see the grid here. So we have option to choose from different algorithms: A-star Manhattan, A-star Euclidean, BFS and uniform cost, and we can generate new obstacles, we can clear the path, and we can start the search. We can control the speed also, and the metrics of the algorithm are displayed here. So let us these are the obstacles we have created, and this is our start and goal. So if we click on start search using A-star Manhattan, so the matrix is given here. Path length is 19, path cost is 18, the nodes explode 57, and execution time is 6212 milliseconds. So if we use the A-star Euclidean and start the search, we see the path length is reduced, path cost is reduced, and nodes explode is 9, because we are using the diagonal movement in the case of Euclidean. And if we use BFS, so we see the path length is 19 and the execution time is much higher compared to A-star, and we see the uniform cost. So we can see now it is similar to BFS, and the metrics are given here. So now if we go to the code, we see we have used the a node which is having a position, a G cost, and the heuristic cost, path cost, heuristic cost, and the total cost, and the parent to track the path. Then this is the path planning visualizer with the metrics listed here. So we have a grid, and we define the cell, we define the start position, we define the goal position, we set up the user interface, we have different buttons and the speed scale, different labels, and the matrix grid is being displayed here. Then we create a canvas and we draw the grid here. So different colors are given to represent different items in the grid, like black is used to denote the obstacles. So we generate the obstacles So we generate the obstacles. After generating the obstacles, so we clear the path, we clear the matrix, we clear everything except the obstacles. Then we use the Manhattan distance formula. We use the Euclidean distance formula, and we get the neighbors if the diagonal is allowed. So we make these moves. We return the neighbors, then we reconstruct the path, we update the matrix, we calculate the matrix, we calculate the path cost here, and in the start search, so we use the different algorithms. So self.bfs step, self.s star step, and self.uniform cost step allows us to use the different algorithms here. It is given here. So step search, and in the S star step we call the algorithm, we use the priority queue, and in the so G cost is calculated and the heuristic is calculated accordingly. So in the BFS step, similarly, we perform the different operations here, and in the uniform cost step and then we create a canvas. On canvas click, and then we start our path planning visualizer. So this is a path planning visualizer module. We can do the path planning for a robot. So these are the different functions involved in this. So thank you all.